Okay, so are we at the beginning or are we at the end for this paradigm of building large end-to-end models in computer vision? Large language models have completely taken over NLP, right? And these models are unified models that can perform many, many different tasks. Some out of the box, some with a small description, and some with just a handful of few examples in context without any gradient updates. And these models are what we call general purpose models. And when I use the term general purpose, I often think about three tenets or three principles of being general purpose. First, they have unified architectures that support many, many different tasks. And importantly, if you want to perform a new task, you don't need to introduce any new parameters, any new custom linear layers or anything like that. Second, these models are able to generalize concepts across skills, which means these models are very good at acquiring concept knowledge or expanding their vocabularies from a certain set of tasks. And then if you teach them a new set of tasks, they're able to transfer this concept knowledge to the new tasks that they have recently learned to perform. And the third tenet, of course, is that these models are extremely efficient at learning new tasks. And now we know for the last few years that language models exhibit each of these three principles to some extent. What about computer vision? Well, the story in computer vision is a bit different. And unification has been extremely hard in computer vision, partly owing to the fact that there's a lot of heterogeneity. So if you take a single image, there's so many different kinds of information that we are interested in parsing, right? So sometimes we want to write a caption, which is producing language. Sometimes we want to draw bounding boxes. Sometimes we want to produce more continuous outputs like depth maps and so on. Some of our tasks require multiple of these outputs together. And of course, we don't stop right there. We go from structured inputs back into pixel space for many of our tasks. And I'm only talking about images here. But computer vision is so much more. There's video, there's audio, there's stereo, there's 3D, and so on. So when there's so much heterogeneity, how can we train and how can we architect models that are as capable and as creative, and importantly, as general purpose as language counterparts? There has been many, many decades of research in computer vision in creating specialized systems. And these are systems that are architected very, very carefully to be extremely performant at a single task. Then, of course, there's also been a lot of research, particularly in the last couple of decades, on training multitask models. And these models are designed to perform more than one task, but often they're designed to perform 2, 3, 4 tasks. There's one common thing in both of these types of models. Firstly, they're designed for very few tasks, but importantly, every time you want to take any of these models and extend their capability to a new task, you must introduce, let's say, a new task head or new deconv layers or a new linear layer. Essentially, add new parameters to the model. And this is not just true of the old way of training. Even in the pre-training era, even in the large data era, models tend to be architected in this way, using task-specialized architectures. And so how do we move away from this? This seems very far away from general purpose models. So how do we move away from this and get closer to models that resemble the capabilities of LLMs? So when I'm talking about task-specific architectures, this is, sort of, I'm simplifying things a bit here, but this is typically how models in computer vision look like, right? You take some input, often an image or some text along with it, right? You have some core network parameters, and then you have these task-specific heads. In computer vision, actually, it gets a little bit sillier than this. It's not just task-specific heads, but it's often data-specific heads. So if you want to do well on COCO detection, you have a particular output head for COCO. If you want to do well on, let's say, the previous data sets like Pascal, you'd have an output head for Pascal. And then, of course, if you want to support more data sets, if you want to support more tasks, often you have to introduce a new set of parameters. One way to move beyond this is really to rethink architectures in computer vision and go from task-specific architectures to modality-specific architectures. So what you're seeing here is that there's some core network parameters which are cross-modal in nature, but then really these models have modality-specific input parameters and modality-specific output parameters. And so as long as the new tasks that you want to learn are still within the modalities that a model supports, no new parameters are needed. So that's one advantage. The second is there's a lot more sharing of parameters across tasks and across data sets. So towards this sort of progress in building general purpose models, about 18 months ago, we released a couple of models, a family of models called the GPV family of models. And I'm not going to go into the technical detail of this model, but suffice to say that this was built modality specific. And these models allowed us to sort of perform many, many different tasks with a single set of parameters. What that really gives you is an ability to do factorized learning, which means that you can now learn skills and concepts in a factorized way. So you can learn skills through more traditional computer vision datasets, like COCO, for example. So COCO has lots of annotations, but for very few concepts, just 80 concepts. It has annotations for detection and segmentation and so on. But we really want these models to learn a lot more about the world. And this does not require us to scale up COCO to millions and millions of annotations. Instead, we can learn skills from COCO, and then we can learn concepts from the web. For example, in this work, we learned concepts from Bing image search. And this, of course, can allow us to scale up the capabilities of these models from 80 concepts to as many as you can download from the internet. And so we demonstrated this on about 10,000 concepts. Not only does this allow you to scale up concepts, but it allows you to perform skills where data simply does not exist for concepts. So a lot of computer vision datasets, of course, were created pre-COVID, right? And so there aren't any examples in COCO or any of these traditional computer vision datasets about, COVID masks and COVID tests and people taking temperatures and people wearing PPEs and so on. But this information does exist on the internet without any labels. And factorized learning allows you to create models that can answer questions and write captions and do detection on all of these newly emerging concepts. So this feels like an important first step, moving away from task-specific architectures to modality-specific models. But we're still far away from GPVs. So how do we get to the next step? How do we move beyond modality-specific parameters? And towards that, I'm going to talk about a model that we recently released earlier this year called Unified I/O. Unified I/O really, the schematic of Unified I/O really resembles a language model. It takes in a long sequence of tokens, and it produces a long sequence of tokens. And of course, these tokens are not just images. These tokens can be all kinds of data. So Unified I/O can input language, it can input images, it can input bounding boxes, it can input segmentation masks, and it can do the same at the output. So it can output language, which is what a lot of multimodal models do, but it can also output depth masks and binary masks and surface normals and more. And it does this with a single set of shared parameters. And that allows Unified I/O to support many, many different tasks across computer vision as well as NLP. So how does this work? So at the heart of Unified I/O is a transformer encoder-decoder architecture. And so if you want to perform an NLP task, it's like any other language model, right? You input a discrete set of tokens about your task, about your instruction, and you train it with your loss, with your cross-entropy loss, with your output tokens. And this is the same for vision and language tasks, where the input is an image and an instruction, and the output is language. And I think we all understand this fairly well. Things get a bit more interesting when you want to perform a task like segment the cat. And that's because the output now is not language. The output is a binary mask. And so the way to do this, or the way we do this, is to not predict pixels, but instead first compress the image or serialize the image into a set of discrete tokens. And there are many ways to get a serialized representation of an image, and using a vector quantized VAE is one such method. Now, VQ VAEs were not developed in order to build Unified I/O. There's a very rich history of serialization techniques in computer vision. VQ VAEs are one such technique which perform really well and compress images really well. And so now when you're training a transformer decoder, if you want to predict a binary mask, What you need to do instead is to predict the discrete sequence that corresponds to a binary mask. And then once your model predicts this sequence, then you simply use a off-the-shelf VQVA decoder in order to get back the original image. So, of course, this trick, I'm demonstrating this only on a binary mask, but this trick applies more broadly. Anything that you can serialize and deserialize can now be supported by unified I/O. And so now you can do things like depth masks, and you can do things like bounding boxes, and so on and so forth. Unified I/O is pre-trained on several million image text pairs, and the pre-training objectives are sort of similar to masked objectives in language, except they're multimodal in nature. And so you want to have unimodal objectives in the sense that you have a sentence and you mask out some tokens and you learn to predict those tokens. Same thing with images in the style of MAEs. But then, of course, you can also do this multimodal. So you can mask out some patches of the image and provide the context not just from the remaining patches, but also from the caption and back and forth. And then once we pre-train this model, we then perform massive multitasking. And what this means is that we've got together about 90 different data sets from computer vision with many, many heterogeneous outputs and inputs, and then jointly train this model after pre-training is done on 90 data sets spanning about 21 tasks. I'm not going to provide any quantitative results here. Feel free to look it up online. But I'm going to show you the kinds of things that a single set of parameters can now do. And so, first of all, you can generate images, right? And so you can generate images from text, but you can also do things like, I'm going to mask out an image, and then I'm going to say fill in the blank region with a train. It puts a train there. You can, of course, input segmentations and get an image output. You can input an image and get surface normal output. You can then start generating structures. You can generate bounding boxes for referring expressions, object detection. You can also get human pose estimates. And of course, you can generate language, which is what even the GPV family of models was able to do. So this feels like the next step up, right? So now we went from task-specific models to modality models, and now to unified models. But of course, unified I/O could only support images and text and representations that were sort of in the pixel space. Can this scale up? Can we start supporting more modalities? And importantly, can we start creating models in computer vision that not just support tasks or data sets, but can really perform tasks that they have never seen in training, similar to what language models are able to do? And towards that goal, we're currently building out the second generation of unified I/O, which is unified I/O 2.0. So one caveat about this is that we're currently actually pre-training unified I/O 2.0. We've barely started doing any sort of instruction fine-tuning. So everything that I tell you here is in flux, and I'll show you some early preliminary results, but that could change as early as next week. So unified I/O 2.0 resembles in its architecture, it's very similar to unified I/O 1.0. But of course, there are many sort of technical details that were brought up in earlier talks today on how to train models at scale. And we also face the same problems. Of course, we have multimodal inputs and outputs to deal with, and so even simple things like tokenization become huge pain points for us. Data cleanup is a huge issue, which previous speakers have alluded to. So unified I/O 2.0 can accept a single image, but now it can also accept audio. And importantly, it can also accept a sequence of images or a sequence of audio spectrograms in addition to language. Now, going from a single image to a sequence of images suddenly expands your capability to video. But it also expands your capability to embodied AI. Because in embodied AI, you want a robot performing, following instructions in an environment. And at every time step, the robot gets a new observation. And so over time, the robot must decide what action to take, whether I should move forward, whether I should move my arm down. And to do this, it must not just take its current observation, but it must take its previous observations as well as its previous actions. And so getting into image history and audio history allows us to tackle embodied AI tasks. At the output, there's three kinds of tokens. There's, of course, text tokens. And text tokens support more than just text. They can support bounding boxes and key points and robot actions. And then, of course, you have audio tokens that can produce audio. And then you have image tokens that can produce all kinds of outputs that can fit into pixel space. Pre-training with so many different modalities gets a lot more complex very fast. And of course, we have the usual masking objectives, but these can be made a bit more interesting in order to inform the model about different kinds of information. So for example, we do have masked image prediction, but now instead of just providing a single image, what you can start doing is providing two views of the same scene. So what you're seeing here on the left is a masked image, and the model must learn to infer what might be behind that mask, but it has access to a different view of the scene. In a sense, you're informing the model about the 3D nature of the world. So this allows you to pre-train models that might be capable at performing some sort of 3D reconstruction tasks or 3D aware tasks downstream. Then, of course, you can take advantage of history. So, for example, if you want to do audio generation, you'd not just provide the current image, but you can provide a history of the audio and the video. And of course, this can inform you what the style of the speaker might be, what the background noise is, and so on. And so the model really must take many cues into consideration in order to perform the task. Then, of course, you can do pre-training with embodied AI environments. So what I'm showing you here is a sequence of observations that the robot has seen, a sequence of actions, and then a next action. And then what the model must now do is synthesize what its next observation might be if it took that action. And of course, there's many other pre-training objectives in sort of this direction. Instruction fine-tuning is also quite interesting for Unified I/O 2.0 because our goals and our objectives are a bit different. So of course, you can sort of take, we were doing 90 data sets, and you can scale this up to 200 data sets. Right? But really, our goal is not just to support these data sets. Our goal is to see if we can generalize to new tasks. In language, this is done with extremely expensive data sets for instruction fine-tuning. Right? And already in language, this is very, very tedious and expensive to collect. And when we were looking at sort of purchasing this data, it was clear to us that this was sort of this was going to get exponentially more expensive as we added more modalities. And so instead, what we've decided to do is look at ways of converting today's data sets into instruction data sets as a first step towards training such models. Now, this is not new in our field. There's a lot of people and there's lots of research groups thinking about this. And here are 3 data sets that people have put out, right? But these data sets tend to be in the image generation space. So there's, of course, instruct pix to pix, which takes an image, and then you have an instruction in order to convert the image into a different style, and so you get this paired training data. Then there's Magic Brush, which has a lot more human intervention in terms of collecting data. And then there's another very sort of interesting way of generating training data, which is take an image, run a model on it, and then invert it, and then say, now that's the task. And this is similar to what Amir was talking about yesterday. So there's another way of generating some interesting instruction tuning data. I'm going to provide you with one quick example. So let's take detection, right? So you could have a vanilla object detection task which says, detect all the objects in this image. But then you could start making this a little bit more interesting. First, you could say, detect objects and use this particular output format. And we see that language model instruction data is full of such things, right? Take this data and convert it into some HTML and use these HTML tags. So this is starting to force models to read the instruction. But then you could say detect all carnivores in the image, which means the model must not just detect animals, but it must also look at its knowledge base from pre-training to say which of these animals are carnivores and only output those bounding boxes. Or you could say detect all objects which have multiple instances from that category, which now forces the model to not just detect boxes, but also do some counting. And of course, you can come up with many such creative ways of expanding today's computer vision datasets into instruction fine-tuning datasets. So as I promised, I just have a handful of early checkpoint results. So we're about halfway through in pre-training, in the latest round of pre-training till we find our latest bugs. And then we've done a little bit of pre-training and just a little bit of fine-tuning on some preliminary data. So of course, here's an input image, and you can of course describe this image briefly, and this is a very simple captioning task. If basic captioning doesn't work, then you know that you have a big bug. But then you can also, just like a language model, you can start giving it some, you can inform it of the style the caption should have. And so you can say, provide a detailed description, share your personal impressions of the scene. And just like a language model, it's able to, provide a nice description of the scene and add, some color to this caption. Then, of course, you can say, you can ask this model to alter the image, right? So here I've asked it to remove the dock, which means it can do object deletion. You can do style transfer. You can say, imagine you're Van Gogh and paint this image. You can add some, fun elements to this, like an aurora. You can render a sunset. Then, of course, you can generate music for this scene. So you can say, well, based on this scene, can you generate a 4-second clip for me? Are you able to hear this? Yeah? So you can generate music for this scene. Then, of course, what you can do is you can say, well, I want you to make this image haunted, and then I want you to generate music for this scene. So now it's sort of, you can see that it's starting to do something interesting with multiple modalities. Now here's an interesting task where the left is the input image, and the instruction is to take a few steps in this scene. It has never seen this scene before. And what it's supposed to do is take a few steps and synthesize what that scene might look like. You can start seeing two things. One, it has learned to, that usually when robots navigate, they sort of don't bang into walls. They sort of go towards the middle of the room. Sometimes they can go from room to room. They go through doors, and it has learned that. And then, of course, it has learned what adjoining rooms look like. And you can see that there's a little bit of degradation in the style, which means that in the first image, the doors are all wooden colored. But as you go through the scene, it gets a bit more modern. But you can see that the model has learned how to sort of synthesize multiple frames into the future, which is quite interesting to see. And then, of course, you have ways of like conversing with this model. Just like language models, you can say, well, here's an image. You can take an image from your cell phone and say, is it going to rain in the next hour, and so on. So Unified I/O 2.0 is quite exciting, and hopefully we'll be able to release it in the next couple of months. And so what I've spoken about till now, and what a lot of speakers have been talking about, is how to scale up models, right? How do you add more capabilities into models, particularly multimodal models, which seem to be, still sort of suffering from this extreme heterogeneity in our tasks. But one thing's clear, this way of doing things is adding more parameters, is adding more data, is adding more compute. And so one of the questions that we've been asking ourselves is there an alternative? Can we create general purpose vision by adding less data, by adding less learning, and instead leveraging specialized models? And this is the paradigm of visual programming. So in order to motivate visual programming, I want to use an example. So imagine you've created a general purpose model, right, for computer vision. The kind of task that users seem to provide language models, and what I think they might ask a vision model, is something like this. So tag this image with characters from this TV show, right, The Big Bang Theory. And so in order to do this, the model is going to have to, detect all the faces, right? Then look at its knowledge base to see who are the characters in this TV show, and then associate those characters with the actors and their faces, and then finally match which actor is which face in this image, and then finally render this image with bounding boxes on the pixel space and render text. And what we're trying to do in the previous paradigm is basically get an end-to-end model to do this quite complex task, right? And so you're going to shove in the image, you're going to shove in the instruction, and you're going to give it to a large neural network, and you're going to hope that this neural network can perform this task. And in order to do this task, a model like Unified I/O or some other model created by someone else is going to have to acquire these 5 different skills that I just listed out, right? Face detection, knowledge retrieval, so on and so on. And finally, it is going to have to learn how to do plotting. But of course, these are just 5 skills for this one task. We know that users are extremely creative in the kinds of tasks that they've been asking ChatGPT to do. And you can imagine that this creativity is going to go through the roof when we start playing with multimodal models, right? So you might want to edit your images, you might want to go through your photograph collections in order to find some images, and so on. And so really, this model is not going to have to learn 5 skills. It's going to have to learn tens and tens or hundreds of different skills. And not only is this model going to have to learn these skills, but it's going to have to chain these skills, and it's going to have to update its skills and update its knowledge base. And so this seems quite challenging. It seems quite daunting, right? So let's take a step back and think about how someone in this audience, a graduate student in this audience, might perform this task. Well, if I asked any of the graduate students here who have any basic knowledge or just playing around with computer vision, actually this task is it's going to take you about 15 minutes, right? You're going to be able to write a program that does 3 kinds of things. You're going to have to, you're probably going to go and import some models, let's say from Hugging Face, right? And then you're going to think about the sequence of steps that are outlined, and you're going to have some basic invocation of these models from Hugging Face, and you're going to pass this image through these steps. And then, of course, at the very bottom, what I'm showing you is some very basic boilerplate code that accepts the input from a user, passes it to the program, and displays the output. These programs are extremely simple to write, but getting models to do this end-to-end seems quite complex. But this program suggests an alternative. Instead of creating an end-to-end model and teaching it all different tasks, why not instead write a program that simply invokes all of these different skills that specialized models already seem to exhibit? And so if you want to do this tagging task, you'll write the program tag characters.py that I just showed you, and you'll take your image and pass it through that program. And if you want to perform a different task, you're going to have to alter your program a different way. And when you alter your program, of course, you're going to have to invoke a different set of models, presumably from some library, right? But of course, you don't want to do this manually every time a user request comes in. You want to do this automatically, right? You want to look at the instruction that the user wants and generate this program automatically. And this is the paradigm of visual programming. So in visual programming, the idea is to accept a description of the task that the user wants and use a program generator to generate a program. And then you want to take the inputs from the user, execute that program, and then display the outputs with some front-end code. Now, in the paper that we recently presented at CVPR, we also introduced an instantiation of visual programming, which was called VisProg. So our instantiation of visual programming uses large language models in order to produce the program and uses some basic Python and some boilerplate front-end code in order to display the outputs. But of course, I want to stress that there are many different ways of performing visual programming. Language models do seem like a very easy, accessible way to do it, which is why we use them in VisProg. At the heart of VisProg are the different models, or the different modules that really are the foundations on which you stand on, right? And VisProg supports models from Hugging Face and PyTorch vision libraries and TensorFlow and so on. It also supports sort of more traditional libraries that I used to use as a graduate student, which was like OpenCV. And really, any program that can be cleanly executed can be supported in this paradigm of visual programming. The programs in VisProg are extremely simple. They can accept an arbitrary number of inputs. In this example I'm going to show you, it's just a very simple example, illustrative example with one input, which is the image. Each line is an invocation of a VisProg module. VisProg modules can accept different kinds of arguments. Some of them are just strings or numbers that the program generator has decided to put into the program that are important for the task. And some are just outputs of previous execution steps. And then when you run this program, you get the output that must be shown to the user. And so one way to get this program is simply to ask a language model. But it turns out if you just ask a language model, I'm saying GPT-3 here because this work was done at the end of last year. Things have moved a lot. But these things still tend to hold. If you ask a language model to generate the program, you get something that's undesirable. And that's because the language model doesn't know what you're trying to do. It doesn't know the context of your task. It doesn't know the modules that you currently support. And so one way to do that is to provide some in-context examples. And as we know, this works exceedingly well. And so the minute you provide some examples of what you're trying to do, these language models can produce code that you can use in order to process your images. And so I'm going to end with an illustrative example. So here are some famous computer vision researchers that you might know. And I asked WizProg who these people are, and it correctly identified them as Jitendra and Feifei. And then I said, well, can you replace these computer vision celebrities with Hollywood and Bollywood celebrities? And it correctly did that. And then I asked WizProg to sort of zoom in onto Jitendra's face and see if he's wearing glasses. And what's interesting here is that not just that it gets the answer right, but what you're seeing here is a visual rationale. It's a stitching of the inputs and the outputs at every stage of execution, which makes visual programs extremely interpretable and provides the programmer an ability to intervene in the reasoning process. And this, I think, can be extremely useful, particularly as you're building more and more complex visual systems. And so I'm going to end with sort of addressing the question that I posed in the first slide, which is, are we at the beginning or are we at the end for end-to-end vision models? So I think we're just scratching the surface with end-to-end vision models. I think models that are going to be built by the entire community in the paradigm of unified architectures like Unified I/O 1.0 and 2.0 are going to happen. I think we're going to build bigger and bigger models. However, when it comes to like expanding greatly to extremely complex tasks, I think visual programming does hold a lot of promise. And I suspect that at least some systems will start adopting this kind of paradigm. But of course, visual programming as we've introduced it today is very, very basic. And I think there's going to be a few upgrades in the next few months even, right? And some of these upgrades are that today our nodes are specialized systems. And so I sort of portrayed this as completely two different paradigms. But I think they can be somewhere in between. You can start using unified architectures as the nodes in your execution graph, which means your nodes can be a lot more powerful now. Second, program generators themselves can be multimodal. Today, the program generator is only taking the instruction. It doesn't know what the image is. It doesn't know what your collection of images look like or what your video is about. But of course, it's important to know that context in order to produce the program. Third, today's visual programs are static. You create a program, you run it. If it doesn't work, too bad. You can interpret it, but you can't do anything about it. And so I think programs will be dynamically generated. Find the faces, figure out how many people there are. If you did not find the faces, do this other thing to identify the characters. And so this is sort of dynamically generated programs. I think it's going to become very common. And then, of course, we haven't really touched upon the ability to converse with these models in order to fix errors. And I think, as chat models have gotten a lot more capable, I think there's a lot of interesting research that we can do in order to bring it into computer vision paradigms such as these. So I think there's a lot of promise in both of these ways of building computer vision systems. What excites me a lot, we work at the Allen Institute for AI, which is sort of somewhere in between academia and industry. And what this excites us is that there are two ways of thinking about building general purpose models. And one way exploits a lot of resources, and one way is extremely efficient. And in my opinion, it's also quite interesting. And so, based on the resources that you have at your disposal, you can still build extremely capable general systems. And with that, thank you.
Thanks a lot, Ani. Questions for Ani? Yes.
I have a great talk. Thanks a lot. It's really impressive. I have a question, probably more about the beginning of the talk than the second part, but I think it's also related. Is you mentioned a lot of tasks in vision. a lot of these tasks are, I would say, inherited from good old vision, like things like bounding box or segmentation or things like that. Do you feel we still need to solve these tasks, or now we can kind of be a bit more end-to-end? Because usually, we put a bounding box because we want to say something about that object. Now we can say that thing about that object right away. Do you feel we still need, like in the future iteration of your I/O, like how is it going to be?
Yeah, that's a great question. I think a lot of tasks in computer vision are sort of, they're skills, they're not end-to-end tasks. Like, I don't think people really care if it can draw bounding boxes around dogs, but it's still people are interested in seeing, well, are all my 3 dogs in the kitchen or not, right? And so I think one way to think about this is data sets that have all of these different skills can still be valuable in order to teach model skills, which seems almost like factorized learning skill by skill. But of course, instruction fine-tuning is going to have to be with, as aligned as possible to the end goals, which is also the same thing with language. So yeah, I don't think we should be evaluating these models at the very end on how they do well at today's benchmarks. I think computer vision is slowly getting past that, but I think the data is still valuable.
So in some sense, using Coco as the instruction fine-tuning kind of...
Coco as, well, maybe there's 3 stages, right? There's pre-training, and then there's skill fine-tuning, and then there's real task fine-tuning.
If you have questions, we can take one more, I think, after this one. So
Thank you for your talk. Just specifically, I have 3 questions.
No more questions after this.
No, they're going to be very specific. So for your transformer decoder, I think it was for the unified I/O, did that have task-specific decoders, or did it also have like the deserialization within it? Because it gave an output of sequences.
No, there's no deserialization within the unified I/O decoder. Unified I/O decoder produces a distribution over all of your vocabulary. And some of that vocabulary is language tokens from like sentence piece encoders, and some of them are visual tokens from your VQVAE, and some of them are audio tokens in Unified I/O 2.0. And so you just have a probability distribution over all your tokens, you sample it, and then based on what the tokens are, whether it is from image domain or language domain or bounding box domain, you give it to the correct deserialization. And of course, there are some tricks to make sure that you don't get a lot of garbage. You have to sort of sample in the right way.
Yeah. And the second one is like the pre-training data. I reckon it's going to be huge for, say, the audio history and the image history that you were talking about. So how big is the pre-training data, and did you like completely do that from scratch for the Unified 2.0? And also a follow-up would be, which is a third question to that, because it's so much of data, even for the invocation function, like the one that you're invoking, is that applicable to edge devices or say a robot when you're just invoking even a function or two for a given task? Can be applicable here.
So the second question was about the dataset size for pre-training. Yeah, the pre-training data, especially when you go to, everyone working on multimodal systems, right, knows that as you get into image space, like dataset sizes in terms of the number of bytes is extremely large. When we talk about history, we're not talking about 30 frames a second. So a lot of work, fortunately or rather unfortunately, in video happens at 4 frames, 8 frames. So we're not talking about thousands of frames of history. We're talking about 4 frames, 8 frames, which will magnify your data an order of magnitude. It's still very large. It's still very difficult to maintain. I didn't quite understand the third question. Was it something to do with visual programming because you used the word invocation?
Yeah.
Sorry, just to, Neil, if you want to set up in the meantime, I think we can use the...
Just finding whether it would be applicable for some edge devices, given even if you invoke, and that's reducing the number of parameters and data, would that be doable?
I see.
Yeah.
I see. Well, the short answer is that training is extremely expensive, but inference is a bit cheaper. Having said that, I think when it comes to creating general purpose models for computer vision, I think we're still I hate to say this, but I think we're lagging a little bit behind language models. And so I think we're in the world of, can we get these models to do interesting things even if they're slow? And once we can prove that they can do interesting things, then we'll start thinking about efficiency on edge devices. So it's a great question, it's a valid question, but I think it's a little too soon.
Thank you. Thank you so much.